Hello, my name is Doğa, and this is my presentation about nanoscience and carbon. So, how's carbon related to nanotechnology? As we know, carbon is a common element which we see everywhere in daily life. Its forms include diamonds, graphites, coal, activated carbon, and carbon black. Millions of tons of these materials are used every year in applications that include abrasives, tires, water treatments, and among others, like we see here in diamonds or coals. These are all related to carbon. So, the carbon we research and use in nanoscience are mostly C60, also known as fullerene, single walled carbon nanotubes, and nanodiamonds. And as we see here, this is a fullerene molecule. And why do we use it? Why do we use carbon in nanoscience? Carbon provides a foundation for addressing some of the most serious challenges facing our world, like demands for alternatives to fossil fuels in energy security and against global warming, drive for efficiency, extend end of life, limit use of exotic materials, and energy efficiency. Access to clean water and air, groundwater and desalination, and mostly needs of an aging population, like healthcare and advanced therapeutics. The new class of carbon materials and chemicals that nanocarbon manufactures will have a greater and more profound effect than existing forms of carbon in shaping solutions to the four challenges listed in the previous page that I just taught. Nanocarbon's innovations are derived from its competency in the chemistry of these new forms of carbon, enabling its customers to shrink the size of next generation semiconductors and make flash memory more energy efficient, provide heavy metal free electrodes for displays, create low cost organic electronic and medical devices, develop low cost solar cells, develop lighter weight and lower cost fuel cells for transportation, make batteries that can be printed, create water filters that won't foul, capture free radicals before they can damage cells, and create X-ray sensors that limit radiation exposure. So, first I'd like to talk about history of fullerene, carbon nanotubes, and nanodiamonds. As we see here, this is a fullerene, and it's a highly unique form of carbon, a molecule at nanometer scale. Fullerenes has been predicted for some time, but after their accidental synthesis in 1985, they were detected in nature and outer space. Although as a molecular material, the credit would go to E.G. Osawa, a Japanese chemist who first proposed its existence a decade earlier, around 1970s. Given its resemblance to the geodesic dome created by Buckminster Fuller, it became known as the Buckminster Fullerene or Fullerene, and later they were mostly called as buckyballs. And a large percentage of academic and popular literature attributes the discovery of hollow, nanometer-sized tubes composed of graphitic carbon to Sumio Iijima of NEC in 1991. Though Iijima has been given much of the credit for discovering carbon nanotubes, it turns out that timeline of carbon nanotubes goes way back, way much earlier than 1991. It goes around 1952, around the time L.V. Radushkevich and V.M. Lukyanovich published clear images of 15 nanometer diameter tubes made of carbon in the Soviet Journal of Physical Chemistry. But um, around that time, the Cold War was happening between Russia and West, so the Soviet press was limited. And nanodiamonds, or diamond nanoparticles in medical use, are diamonds with a size below 1 micrometer. They were mostly first found in 1963 Soviet scientists at the All Union Research Institute of Technical Physics. They noticed that nanodiamonds were created by nuclear explosions that used carbon-based trigger explosives. After this, let's take a look at fullerene. And as we see here, this is a graphene molecule. A fullerene is an allotrope of carbon whose molecule consists of carbon atoms connected by single and double bonds so as to form a closed or partially closed mesh with fused rings of 5 to 7 atoms. The molecule may be a hollow sphere, ellipsoid, tube, or many other shapes and sizes. Graphene, as we see here, is isolated atomic layers of graphite, which is a flat mesh of regular hexagonal rings, can be seen as an extreme member of the family. Fullerenes with a closed mesh topology are informally denoted by the empirical formula Cn, often written Cn, where n is the number of carbon atoms. However, for some values of n, there may be more than one isomer. There are two major families of fullerenes, with fairly distinct properties and applications. The closed buckyballs, Buckminster fullerene, as I told earlier, and the open-ended cylindrical carbon nanotubes. However, hybrid structures exist between those two classes, such as carbon nanobuds, nanotubes capped by hemispherical meshes or larger buckyballs. Buckminster fullerene, or buckyballs to be short, are most common fullerene type, as you see here. There are other types of fullerene. Another fairly common fullerene has empirical formula C70, but fullerenes with 72, 76, 84 and even up to 100 carbon atoms are commonly obtained. The smallest possible fullerene is the dodecahedral C20. There are no fullerenes with 22 vertices. Heterofullerenes have heteroatoms substituting carbons in cage or tube-shaped structures. They were discovered in 1993 and greatly expand the overall fullerene class of compounds. Notable examples include boron, nitrogen, also as a fullerene, oxygen, and phosphorus derivatives. Three-metal sphere carbon nanomaterials comprises 80 carbon atoms, C80, forming a sphere which encloses a complex of 3 metal atoms and 1 nitrogen atom. These fullerenes encapsulate metals, which puts them in a subset referred to as metallofullerenes. Three metal spheres have the potential for one use in diagnosis, as safe imaging agents, therapeutics, and in organic solar cells. And this is a study on heterofullerene molecule. And as I mentioned earlier, this is a 3-metal sphere molecule. Fullerenes are also excellent conductors of heat and electricity, and they possess an astonishing tensile strength. As we see here, this is another example of fullerene. And where do we use fullerene? Fullerenes are active molecules, and that makes fullerene molecules a great antioxidant because it can easily react with radicals due to high affinity of the electron. Accordingly, one of the most important uses of fullerene is medicine, like we see here. They are also used as an anti-aging and anti-damage agent in cosmetic sector because of their unique molecular structure, antioxidant effect, and biological compatibility. Some fullerenes can form conjugates with proteins and DNA. This situation is thought to help to development of anti-cancer treatments. Fullerene molecule can be used in drug delivery area. The surface of fullerene is covered with a chemotherapeutic agent. This agent finds the cancer cell and is transported directly there. Functionalizing the fullerenes aims to increase the solubility of the molecule by the cancer cells. Cancer cells take up these molecules at an increased rate because of an upregulation of transporters in the cancer cell. In this case, amino acid transporters will bring in the L-arginine and L-phenylalanine functional groups of the fullerenes. And as we move up to the carbon nanotubes, we can tell carbon nanotubes, also known as CNTs, are tubes made of carbon with diameters typically measured in nanometers. Carbon nanotubes often refer to single-wall carbon nanotubes with diameters in the range of a nanometer. Single-wall carbon nanotubes are one of the allotropes of carbon, intermediate between fullerene cages and flat graphene. So basically, we can call carbon nanotubes cylindrical fullerenes. Carbon nanotubes are usually only a few nanometers wide, but they can range from less than a micrometer to several millimeters in length. They often have closed ends, but can be open-ended as well. Carbon nanotubes' unique molecular structure results in extraordinary macroscopic properties, including high tensile strength, high electrical conductivity, high ductility, high heat conductivity, and relative chemical inactivity. As we talk about mechanical properties, carbon nanotubes are the strongest and stiffest materials yet discovered in terms of tensile strength and elastic modulus. This strength results from the covalent bonds, sp², formed between the individual carbon atoms, but in the radial direction they are really soft. The electrical properties of carbon nanotubes are either metallic or semiconducting along the tubular axis. It means along this way. They are frequently referred as the one-dimensional conductors. Intrinsic superconductivity has been reported, although other experiments found no evidence of this, leaving the claim a subject of debate. As optical properties, carbon nanotubes have useful absorption, photoluminescence, also fluorescence, and Raman spectroscopy properties. Spectroscopic methods offer the possibility of quick and non-destructive characterization of relatively large amounts of carbon nanotubes, yet the practical use of optical properties are still unclear. And thermal properties of carbon nanotubes are all nanotubes are expected to be very good thermal conductors along the tube, along this way, exhibiting a property known as ballistic conduction, but good insulators lateral to the tube axis. Crystallographic defects strongly affect the tube's thermal properties. These defects highly reduce the thermal conductivity. And where do we use carbon nanotubes? Current use and application of nanotubes has mostly been limited to the use of bulk nanotubes, which is a mass of rather unorganized fragments of nanotubes. We can give examples as bicycle components and mostly flat and riser handlebars along this way, cranks, forks, seat pods and stems and aero bars. We can use the carbon nanotubes mostly anywhere on the bicycle. And resin. It's been used for wind turbines, marine paints, and a variety of sports gear such as skis, ice hockey sticks, baseball bats, hunting arrows, and surfboards. In this picture, we can see a carbon nanotubes resin covering this baseball bat. And vantablack. Carbon nanotubes are also used to create vantablack, which is one of the darkest substances absorbing nearly all of visible light. And one other use can be probes for atomic force microscope probes, like here. And mostly scaffolds. In tissue engineering, carbon nanotubes can act as scaffolding for bone growth. And lastly, I'd like to talk about nanodiamonds. As we see here in the picture, nanodiamonds or diamond nanoparticles in medical use are diamonds with a size below 1 micrometer. They can be produced by impact events such as an explosion or meteoritic impacts. And the first place they found it was a nuclear explosion event. Because of their inexpensive large-scale synthesis, potential for surface functionalization, and high biocompatibility, nanodiamonds are widely investigated as a potential material in biological and electronic applications, and quantum engineering. In this picture, here's a nanodiamond in a nanoscale with a 10 nanometer. Nanodiamonds have excellent mechanical and optical properties, high surface areas, and tunable surface structures. They are also non-toxic, which makes them well suited to biomedical applications. There are three main aspects in the structure of diamond nanoparticles to be considered: the overall shape, the core, and the surface area. Through multiple diffraction experiments, it's been determined that the overall shape of diamond nanoparticles is either spherical or elliptical. At the core of diamond nanoparticles lies a diamond cage, here we see, which is composed mainly of carbons. While the core closely resembles the structure of a diamond, the surface of diamond nanoparticles actually resembles the structure of graphite, which we have seen earlier. And where do we use nanodiamonds? Because of its construction, nanodiamonds can be highly versatile, but can be used in nearly all branches of science. They are mostly used in microabrasives here, and they share the hardness and chemical stability of visible scale diamonds, making them candidates for applications such as polishes and engine oil additives for improved lubrication. Here is a microscale microabrasive. And in medicine, diamond nanoparticles have the potential to be used in myriad biological applications, and due to their unique properties such as inertness and hardness, nanodiamonds may prove to be a better alternative to the traditional nanomaterials currently utilized to carry drugs, coat implantable materials, and synthesis biosensors and biomedical robots. The low cytotoxicity of diamond nanoparticles affirms their utilization as biologically compatible materials. In drug delivery, diamond nanoparticles of around 5 nanometers in size offer a large accessible surface and tailorable surface chemistry. Nanodiamonds with attached molecules are able to penetrate the blood-brain barrier that isolates the brain from most insults. Here, in drug delivery system, this can be an example. In catalysis, decreasing particle size and functionalizing their surfaces may allow such surface-modified diamond nanoparticles to deliver proteins, which can then provide an alternative to traditional catalysts. This is an example of a catalyst. And in skincare, nanodiamonds are well absorbed by human skin. They also absorb more of the ingredients in skincare products than skin itself. Thus, they cause more of the ingredients here to penetrate the deeper layers of the skin. Nanodiamonds also form strong bonds with water, helping to hydrate the skin. So we can use this mostly in skin masks or stuff like that. And in sensors, naturally occurring defects in nanodiamonds called hydrogen vacancy centers, NV, here, have been used to measure changes over time in weak magnetic fields, much like a compass does with Earth's magnetic field. The sensors can be used at room temperature, and since they consist entirely of carbon, they could be injected into living cells without causing them any harm. Also, nanoscale diamonds can be bent to a local maximum tensile elastic strain in excess of 9%, with the corresponding maximum tensile stress reach around 100 gigapascals, making them ideal for high-performance nanomechanical sensors and NEMS applications. These nitrogen vacancy centers, naturally occurring defects, can also be used in optical and quantum computing. And these are my references. That's all for my presentation.